morning and welcome to this video solution and explanation from NCERT Exemplar. This is from the chapter of semiconductors, probably a chapter which a lot of students find very complicated. This is an advanced level problem, but based on basics. And this is from NCERT Exemplar, so obviously it's a bit complex. The way I'm going to approach this is I'm going to give you steps towards the solution through explanation. So first I will explain you a few things and then finally we will solve the question. But that solving the question is completely dependent on the quality of explanation I will give you. My idea and aim is to impact 1 million students and bring clarity in mind of people. A lot of crap is being taught on YouTube and other places I have seen where there is no explanation, there is nothing, everything is taken for granted. I just want to, share my knowledge and experiences with you. And idea is to bring clarity. The more clarity you have, better, you will feel about physics. So if you read this question, let's read this question first. The breakdown in a reverse biased PN junction diode is more likely to occur. So there is a, a reverse biased PN junction. Okay. The question is, why does a reverse biased PN junction break down? What are the reasons and the factors on which the breakdown of a PN junction diode is dependent on? If you look into the words, a lot of words are, alien, so to say, right? It talks about large velocity of the minority charge carriers. It talks about doping. I'm just highlighting because if you have read breakdown, you will find very elementary level of breakdown has been explained. So doping is very important. Large velocity, strong electric field, the size of depletion region, etc., etc. So if I were to, summarize, the question says, any breakdown could, it's not an answer, could probably depend on large velocity. Okay, so let's say it could depend on large velocity. This is as per the question. Right or wrong, we will decide. Large velocity of the minority carriers, right? Although the question looks a question on the breakdown, it is in fact a very difficult type of question, because if you read the reverse biased PN junction, you will not find anything mentioned in NCERT at least, right? So the second thing they want you to focus on is the doping level, and find the truth of doping level, what exactly is the role of doping when it comes to the breakdown. Then they talk about a strong electric field, okay, in the depletion region, okay, so which means in the where you have the junction barrier, and then you have again strong electric field, and then they link the concept. So strong electric field, two situations are given. You have one which is doping is high, doping comes back, so doping is very high. The second situation being referred to is when the doping is low. Okay, so if you look into the the quality of question, you will get completely puzzled because you would not have read anything about breakdown. So today my job is to demystify this. I can tell you the answer in one line. I will not tell you the answer. Let's go through step-by-step explanation, and this will at least help you solve at least 10 to 20 multiple choice questions you can expect to get in board examination, state board examination, AP physics, SAT physics, CBSE, any board, any part of the world you are there. You will be able to answer at least 10 to 20 questions when it comes to a reverse biased PN junction diode, okay? So I will go in steps. Let me start with the first lesson, which is going to be about what is a PN junction breakdown. Because if you look into the question, breakdown is prominently asked for, right? So it's a reverse bias. So let's first understand what exactly is a junction breakdown. So I'm just going to draw a PN junction, okay? And some important and interesting points I will tell you. This is going to be a full-fledged lecture, which is explanation followed by an answer. I am not in business of giving you answers where you don't learn anything, right? So if you look into a conventional, PN junction diode, I'm just drawing one. Okay, so this is a PN junction diode. It's a very conventional one. What is the best way to use this? Always forward bias this. Okay, so forward bias this. Okay, forward bias. The diagram I have drawn is open circuit, right? So this is an open circuited because I have no battery connected to this. So open circuited PN junction. So this is your P side, right? And you have impurity like boron, and then you have N side impurities like the phosphorus and all that. You can find out pentavalent impurities are there. This is your, I'm giving you very basics right now. I think it has not come in the center. Let me just make it in the center. So this is your junction, and both the sides, what you have is a junction, so to say, the barrier. An electric field exists here because of the ions. You know that immobile ions exist here. And P side has the negative ions, and the N side has the positive ions. Okay, so these are all positive ions and these are all negative ions, right? So there is an electric field which is existing. This is open circuit, and finally what happens is you have all the diffusion happening because this side has more holes, P side has more holes, they diffuse, N side has more electrons, a diffusion happens, they move in the reverse direction, and finally there is a formation of a junction barrier or a depletion region where the recombination happens and immobile ions. So this is open circuit. When you forward bias it, what do? You connect P with P, right? You connect when you talk about a normal mode. And if you know this, you can move forward, but you will know some interesting facts soon. But it is important to start the story from the very beginning. So let's say you have a forward bias, connect P to P, N to N, right? And that is what makes it a forward bias. This is a normal mode. You would like a PN junction diode to work like this, right? This is the way most of the PN junction diodes work. This is forward biased. The P is connected to P. A current starts flowing, okay? And a current starts flowing, right? So current starts flowing and you're very happy with that, right? So this is your forward bias. But the question is on reverse bias, right? So first of all, you understood open circuit. This is without any battery. When you forward bias it, what happens to the junction barrier? The junction barrier, which is here, which you see the width of the junction barrier. Let me show you the width of the junction barrier. For example, in the open circuit, it was here. But when you apply the forward bias, this junction barrier undergoes a change, which is the width of the junction barrier goes down, right? So this is your new width. Okay, let's say now I made it too narrow. It is not that narrow. So let's say earlier the width of the junction potential was this, and now the width of the junction potential is only this much, right? So it narrows and it offers very low resistance. So a forward biased PN junction allows good current to flow through it and has very low resistance. So low resistance, low resistance situation is the key. And then of course a large forward current, right? It's a nice situation or position to be in. Most of the PN junction diodes are used like this, but there are others which are used in reverse bias. We're just coming towards that only. But first of all, let's understand what is forward bias. For those who have never studied semiconductor in their life, they will find it very interesting. But now the level and the concept and the explanation will move towards the next level of resistance. Sorry, the reverse bias, which is a high resistance scenario, and I will explain you why. So it is low resistance, current flows, no problem. The depletion layer, okay, the depletion layer squeezes, it becomes narrow, right? It becomes narrow. So this is your narrow, because the electric field which is provided by the battery cancels the electric field of the which is created due to diffusion. So if this was your electric field, right? So if this was your electric field, now the electric field which you have applied externally, is in the reverse direction. It is in the reverse direction, which is this positive to negative, and therefore it tends to cancel out the electric field which exists due to the immobile ions. So you can see there is a negative side and a positive side, and so this is positive, right? So this is positive, positive, and these are negative, negative. So this electric field is due to the junction and the diffusion process, automatic creation, open circuit. This electric field is due to the battery. So this is external. Okay, E external coming from where? It is coming from the battery. Clear? Very simple, right? Nice situation. And gradually we are moving towards understanding. Now let's talk about reverse bias, because the question has a lot to do with reverse bias. For those who know what is reverse bias and all that, move forward. But again, I'm telling you, you will learn some interesting facts. So it's important that you continue to watch this, but it's your choice. You can move forward if you understand, the lesson one, and I'll gradually progress the way I do generally in my videos. I don't jump to solutions. I don't like that, because explanations are very important. And the crap which is given in YouTube, a lot of that has to be cleared now. Okay. It's time that we change the way physics is studied. So let's talk about another situation. So you have the conventional, which was a PN junction diode. This is open circuited. And now this is what I do. Okay. And don't worry about the width. The width is equal. The junction is right in the center. Sorry if the diagram doesn't look good. And what I'm going to do now is, let me just use the color which is easy on the eyes and use that. Okay, so let's say we bring in, all right, I think this is a pathetic color, and I will just change it. I hope I'm able to change it. Okay, so I think the software is not helping, but hopefully you're able to see something. So this is your, okay, the reverse bias. Okay, so I am now drawing a reverse biased situation. Let's see what happens in a reverse bias. So this is your, okay, it's thicker, right? So it's easy. So I am connecting the negative side to the P side. So this way you can understand the circuits also, how a PN junction diode is to be reverse biased. Very elementary, very basic. But mind you, the question is not elementary. The question is, tough one. Now, because of the external electric field, the junction barrier size increases. Okay, it increases. So let me draw the new junction barrier. So earlier, this is your junction barrier. Same situation. The electric field is in this direction. Finally, we have the color, right? So, and now what will happen is the size of the depletion region will increase, because you have another electric field which is coming to support the electric field which is due to the immobile ions, right? So you have a lot of immobile ions that get produced due to the process of diffusion. If you don't know what is diffusion and drift, please go and watch my YouTube video. Diffusion is when you're open circuit, you bring P and N together, automatically the charge carriers, the majority charge carriers flow, and then finally, they neutralize, and there's a creation of depletion layer, and immobile ions get created there. So let me come back to the point. So this is your external electric field. This is your E external, right? So this is your E external, and this of course was your, the electric field which was internal at the junction. Okay, and you can see the battery is arranged just opposite. So the positive side is connected to the N type, right? And the negative side, which is this, is connected to the P, right? And now, of course, what you will notice is if you have a situation like this, you still see some current. Okay, it is not that the current vanishes. You saw a good large current flowing here. I told you it's a low resistance and a large good amount of forward current. Very happy, right? The electrons and the holes both constitute, so there is a I hole and there is a I electron constituting the current. Now if you go to the second situation, rather third. The first one is open circuit, second is forward bias, the third is the reverse bias. Okay, in the reverse bias, what's happening is the resistance of the circuit goes up. So it's a very high resistance scenario, right? It's not a very comfortable place for you to have current. High, resistance exists, so you have a lot of good high amount of resistance coming in here, and then what happens is you have a situation of a low current, which is a forward current is impossible, right? No forward current will flow. The forward current is because of the majority carriers. Here, what you will note is a very small current which is flowing, and that is because of so there is a small current. It is called a reverse current. Reverse current. Now this is a drift current, okay? And I hope you remember the drift. If you notice, the P side has electrons which are in minority, and the N side has holes in minority. Now if you see carefully, the electric field direction is, from right to left. This is the way electric field has got added. So this is your external electric field, and this is your internal electric field. Both of them have got added, and the size of the depletion region has got added, which means it's very difficult for the majority carriers in P and N to cross this because of the huge number of immobile ions which will exist in the depletion layer. The depletion layer has become so wide. Look at the width, right? So it is huge compared to forward bias, where it became so narrow, right? So you have a narrow depletion layer, is pretty narrow, but has become very large here. So given these circumstances, if you look into the electron is very much attracted towards the positive ions, on the right hand side of the depletion. So the electron, so if you notice, the electron would like to move in this direction, right? And the holes would like to move in this direction. And these are minority, right? So I'm referring to the minority now. This large forward current was because of majority, right? Majority carriers, the holes moved, the electrons moved, which are majority in P and N. But if you talk about the reverse bias, which is what I've done, this is a third situation of reverse bias. And if you know, please move forward, but this will help the students who are just doing a revision, and bring a lot of clarity in your mind. So because of the electric field is from right to left, right? So the electrons are attracted towards this side, and the holes are attracted towards the negative side, because you have a lot of negative ion accumulation here, right? So a lot of negative ion accumulation on this side, and this side you have a lot of positive. So obviously electrons will love to move on the right hand side, right? And the holes would like to move towards the negative ion side, right? So so now what is happening is it's a very small current. It's a very small current, and this is also known as a leakage current, okay? Whatever you may do, you can increase the size of the reverse bias voltage. So for example, you have, some voltage applied here, which is reverse bias, okay? So let me call this VR. You can increase it, but the reverse current really doesn't change, okay? So if I were to summarize, the reverse current is because of the minority carriers, okay? So it is clear in your mind, right? If you read the question, I told you, one of the very important key points in the question has to do with the minority, charge carrier. So you can see in a reverse bias, who is active? In a reverse bias, the minority charge carriers are more active than the majority. Majority anyways is gone, right? You cannot have. So the reverse leakage current, or the small current, is due to the drifting, okay? It's drift. It is not really impacted by the external voltage. So these are drift happens because of the electric field has become reverse. It is preventing the flow of majority flow. Some ions have got accumulated on both the sides, attracting the minority carrier. So minorities are still Charge carriers are still able to move, but now you have a high resistance scenario, right? And you have a drift of current, which is called as a reverse current. Now, we have still not talked about, we have understood reverse bias. I hope the reverse bias is clear. Not a good place, not a good situation to be, because the current is very small, okay? The current, the minority reverse current, which I'm referring to, the current flow due to drift of minority charge carriers. So minority charge carriers are drifting and the reverse current is very, very small. Now, because of this, right, the what is happening is you have a definitely a reverse biased PN junction diode, but it's serving no purpose, right? So you, at the moment, right, the reverse bias has a value, but in the context of the question we're talking about, we're not able to link the question with what I have taught you so far. And soon I will start linking the question with the lesson I started with. Okay, so this lesson has included so far the concept of open circuit PN junction diode, forward bias, and then the reverse bias. And it has explained you that in a reverse bias situation, you have minority charge carriers which play a role, and it's a high resistance scenario. Now comes the real good part of it, right? I'm going to take you towards the concept of the breakdown. Okay, now what happens in a breakdown? Now what happens is, I told you the reverse bias, okay? So every semiconductor, material, for example, silicon and, all these germanium, even after doping, you dope them with phosphorus and you dope them with boron. Now, what happens is the PN junction that gets created because of that, the junction barrier, which is 0.7 volt, etc., 1.1, all those forbidden gaps and junction barriers potential which get created, prevent the flow of current, right, in a reverse bias mode. Now, what I'm going to do is, in a reverse bias mode, I am going to increase the voltage, okay? So I told you, if you increase the reverse bias voltage, the reverse current remains very small. So the reverse current is very small, right? It's very, very small. I told you, increase it further. Okay, so VR1, make it VR2, and I'll tell you why I talked about materials. Okay, so make it VR2, then make it VR3. You will find, no noticeable change in the reverse current. The reverse current remains very small. Okay, it remains very small. So you keep on increasing that voltage, but at a certain voltage, what will happen? And I'm talking about reverse bias voltage. All these voltages which I mentioned are reverse biased voltages. Now let's draw the, so to say, the characteristic diagram. Everybody loves to understand the characteristic diagram, and they ask you a lot of questions on the characteristic. So you have a minor current, and you are in, so this is your reverse biased voltage. A minor current is there which saturates. It doesn't go up after a certain value. Why it doesn't go up, right? It is almost stationary. It doesn't go up because the number of minority carriers is constant, right? So these electrons and holes are not infinite. They're not infinite. There is a limit to the number of minority carriers which exist in PNN. And therefore, you may think that by increasing the reverse bias, the minority carriers would like to, more minority carriers would like to go. But after a while, because the number is very small, they saturate. And therefore, this reverse current is also known as a saturation current. This is also known as a saturation. And now comes the, the climax of this. So at a certain voltage, you keep on increasing. At a certain voltage, you will see that there is a sudden increase in the reverse current. Okay, and we are not talking about like big current. It's a very small current, but compare this to a leakage current, which is like this much, right? It's so small. The leakage current here, and I've drawn even this is even smaller than that. If you enlarge the diagram, if you enlarge this diagram, let me just show you what's happening. Look at this diagram, right? Look at the value. I think, drawn an exaggerated picture. Let me just rub this off so that you can really appreciate What is the magnitude I'm talking about? I'm talking about such a small reverse leakage current, and so it saturates, it doesn't increase even if the voltage is going on increasing towards the left, reverse bias. And then you see there is this bend which is coming. Okay, this is the bend being referred to, right? This is called as a knee. And from this point onwards, what you see is a large rush of current. Okay, this large rush of current, right? You see that without increasing the, so you do see, right, that the reverse voltage failed to increase the current, but from the knee point onwards, right? So this is the knee, right? You have a knee, your legs have two knees, right? So this is your knee, and then there is a exponential increase in the current, but the voltage, reverse voltage, has not gone up tremendously. But in this region, if you see a minor increase in the reverse bias or reverse biased voltage, has increased the current exponentially. This is a nice situation to be in, right? So in a general reverse bias, you're here, right? You have hardly any current, you saturate it, right? And good for nothing, right? You just reverse biased. And if you see, most of your understanding is this is reverse bias, and then the leftward knee happens, knee point, and then sudden rush of current, and this is the current in the reverse directions, right? So this is your, now you have a good situation. You have a situation where just like a forward bias where the current is high, the current is high also. So the current is high. Now the I is pretty good, is high. Okay, it's high. And what is the other thing you notice? The resistance is lowered, right? Compared to this point, right? Where you are in reverse bias. So in fact, your current resistance is so low that without increasing further voltage, you're able to get so much current, which is very nice, right? So resistance, which is very dynamic. This semiconductors do not follow Ohm's law, but they definitely have an instantaneous value of resistance calculated by dV by dr. So you can use the, dV by di, I'm sorry. So you can use the slopes, of the graph and find out. You can get numericals on this. Anyway, we will talk about these type of numericals later. And this is called dynamic resistance, like unlike a metal which has a fixed resistance at a temperature. So the current has become very high. This is called as the situation of the breakdown. The point, the knee point after which you see the value of the current rising is the breakdown region. So we say if this is the region where the diode is operating, we will call it the breakdown region. Okay, so this is called the breakdown of the PN junction, right? I hope this is clear. Breakdown of PN junction has happened now. There is an increase in current suddenly. I hope this is making sense, right? Why this sudden increase in the current? We will talk about it. But right now, this is a phenomena which is observed after a certain value of the resistance. There is an increase of the current. Why this current increases? Let's talk about it. But I hope the concept of breakdown is clear. The breakdown happens when there is a sudden rush in the reverse direction. Breakdown does not happen in the forward bias. The breakdown happens in the reverse biased situation. Very basic. If you know this, you can move forward. Let's talk about the reasoning of why the current, which was at saturation point, very low amount of current flowing. Suddenly, when you increase the value of the reverse biased voltage, why the current increased at this level. So let's talk about the reasoning now. All right, so let's understand the reason for the breakdown or the sudden rush of current. So let me help you understand that. Let me draw the PN junction diode so that you can understand what's happening inside the. And I told you, if you watch this video, listen through this, you will be at least able to answer 10 to 20, reverse bias questions, because I'm going to give you some very important insights into stuff which you may not have heard or ever, thought about. So let's say, we are referring to the situation of where you have a reverse bias. So a large, you know, so to say, a large depletion layer, and then junction. So it's a wide one, and of course, I am drawing the. So this is your P side of things, and this is your right. This is your N side of things, right? So this is your. So I'm going to make it negatively biased. So this is the negative bias I apply, and the negative bias, okay, is what matters. So I'm I'm telling you the circuit. Now, why the breakdown happens? What happens is, I told you the electric field, okay, the electric field becomes very high in this region because the electric field is external, right? So you have an external electric field which is working coming from the battery. And then, of course, you have an internal electric field also by virtue of the junction that gets created, right? So two things happen. And you know that you have some negative ions here, right? And I'm going to concentrate on this. I'm showing very few negative ions, so let's say, there is only single layer. For simplicity, you can have, and then I'm going to draw the negative ions of the N-type impurity, which could be a phosphorus ion. This could, on the left-hand side, you could have a boron ion, right? So these are, negative, right? These are negative, 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 negative. And these are positive, 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 right? So look into this. The ions are the focus now. Don't worry about the minority carriers which are contributing. This is what will happen. When you increase the reverse bias, the electric field goes up, right? The electric field value goes up tremendously. So if you've done electrostatics, you already know that E is given by minus dV by dx, right? So as you increase the voltage, the electric field, which is the sum of the electric field, which is external, electric field, which is external, electric field, which is external coming from the battery, and of course the internal electric field because of the ions. What it does is it strips off these ions. So these are the ions that you see, right? These are the ions. So these are the ions being referred to. The strong electric field, okay? The strong electric field, strong electric field strips off the valence electrons. So there are valence electrons left. Once you have those, so right, valence electrons are the ones that participate in formation of covalent bond, right? So those valence electrons so get stripped off. They get removed from the ion. So if you have a boron ion or a phosphorus ion, the electric field is so strong now during the this particular place, which is you have increased the value of your reverse bias to a value to such a large extent that a very, very strong electric field has got, and it strips off, a strong electric field strips off the electrons, okay, strips off valence electrons from the ions, okay, from the ions. And I'm just referring to the ions which are there in the depletion layer, right? These electrons which you have stripped off, okay, and let me just show you and draw the diagram now. So the electrons which get stripped off, so for example, this is an ion, you get an electron from it, right? So I don't know why the color is not changing, but let me give it another try to so that you can see the electrons clearly. And I will just enlarge the diagram, okay? Let me just enlarge the diagram so that you get more clarity and you can see it from close, right? You can see a reverse biased, a very wide depletion region. How is that what happens? What's happening, which is increasing the current? So you have this electrons, which are getting created, electron, 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 electron. So the electrons are coming from where are they coming from? They're coming from the depletion region itself. In the depletion region, you have electrons which are, getting created because of the strong electric field. And these electrons, obviously, right, if you see the battery, will get attracted towards the positive side of the battery, right? So they are getting attracted towards this side, right, which is from left to right. Okay, so they're coming from where? They're coming from the depletion layer, right? So the current direction. So these are the electrons which are getting attracted towards the. I'm drawing a minus sign on top of them. I don't need to, but the direction of the current is this, right? Which is the direction of the drift current also, right? So the minority charge leakage current is in this direction, and now it has got an additional partner, which is a strong rush of electrons coming in and helping it out. And this is the reason, this extra current that gets created because of these electrons. So this is your, the standard saturation current, which is, which gets saturated because of the limitation of number of the minority holes in the either side. So both the sides have limited number of minority carriers, limited current, so called saturation current. Now you have a friend, which is the strong electric field comes in, it strips off the electrons from those ions. The stripping off results in a strong flow of current. And now you can see a strong current will flow. And this region is called as the breakdown. So what you see as a breakdown here, right, which I have just shown you, is the resultant of these current. These electrons. These electrons are the ones which are responsible for this. Okay, they're stripped from the mobile ions. So I hope now you have got clarity on why the breakdown region behaves that way, from where the current comes from. And mind you, the examiner is testing you. I will take you back to the question. The examiner is going to test you when a question of this level comes in. I told you will be able to answer 10, 20 more multiple choice questions because of the clarity you will get on the reverse biased PN junction diode. But the keywords, the minority, which we refer to doping, have still not come. So I hope so far what you've learned, right, which I told you, the first part of the whole explanation will dwell on the concept of what is a PN junction diode breakdown. So I hope the concept of junction breakdown is clear to you. If I did not spend any time with you to explain this, then you will not be able to understand the answer of this question. Okay, this is the question which looks very innocent type of question, but unless you know the details of a reverse biasing, you will not be able to go inside and understand what is the what is that the examiner is trying to ask you. The examiner is trying to assess you on a lot of things. Okay, doping is one, the strong electric field, etc., etc., right? So nothing straightforward, but if you start seeing, let's talk about choice number C and D, right? The strong electric field in the depletion. So I concentrated on depletion region. I did. I concentrated on a strong electric field. I did. So far, if you look into the last phase of the video where I just discussed the breakdown and sudden rush of current, I did talk about strong electric field. I talked about depletion region. What I did not probably talk about is doping, how doping impacts the whole thing, which is the breakdown. We have not talked about it. We've also not talked about large velocity and stuff like that. So as we progress, you will start understanding. So let me move to the next part of the video, which is focused on the concept of doping. Okay, we will learn something about doping, how the doping is associated with this whole thing, how doping impacts breakdown. We have so far understood the source of extra current which comes in, but we have yet to understand what is the doping thing doing here. So let me start the next lesson, which is the lesson on what is the impact of doping on a reverse biased PN junction diode. Thank you very much. All right, so let's talk about doping. Okay, and this is very important in the context of breakdown of a PN junction diode. That is why we are learning doping today. And what is the impact of doping? So let's take a ordinary diode, and this is your ordinary PN junction diode. Okay, this is your ordinary PN junction diode, and I am going to show you what happens when the doping concentration increases. So this is your normal doped. So the doping here is normal on the P side and N side, right? Now what I do is, so this is normal doping, okay? Figure number one, which you see, belongs to what I will call as a normal doping. This is nothing spectacular like. So this is your normal doping levels. And the second figure I want to draw is this one. Okay, so let's talk about the second one, where what I do is I heavily dope it, which means I add a lot of impurity levels on P side and N side respectively. So they're pretty heavy. And you know the acceptor level and donor level, right? The energy level, which is just below the conduction band and just above the valence band for a acceptor level, right? So you have to understand acceptor level and donor level generally. Also, we are not going to talk about it. We are just concentrating on the impact of doping right now. Okay, so now if you look into ordinary versus a heavily doped, so this is your heavily doped. Okay, this is your heavily doped material. Okay, so this is heavily doped PN junction. You have a junction like any other junction, but let me concentrate on the let me just concentrate on the left side. On the left side, if you remember, you always have a right, you have a lot of ions. So P side has what? A P side. I'm drawing smaller ones because this business of drawing ions wastes a lot of time. So P side has negative ions, and the N side has immobile, which are plus, right? So you have a lot of pluses here. Now when you apply the reverse bias, okay, when you apply a reverse bias to an ordinary, so this is open circuit first, and then you applied a reverse bias to it, right? So you apply a reverse bias. First it was ordinary, right? So this is ordinary, and this is your reverse biased one. Okay, on the right hand side, what you see is heavily doped. It is ordinary, and this is heavily doped, right? So once you see, what happens is, once you reverse bias this, right, and say this is it, right? So this is so I'm talking about depletion layer. Okay, depletion layer. So what happens here is the process of diffusion does happen. Okay, so this is your P side, and it is still in the state of open circuit. I'm not connecting any reverse bias on this. We will talk about that. So now what is happening is the electrons are diffusing on this side, and the holes are diffusing to this side, right? Which is very standard, right? This is what happens when a junction diode creation happens, right? This is open circuit, no battery connected. And then what happens is you do have a creation of, finally this is what happens. It settles like it does on the left side of the figure, and you have ions which exist on the left and right hand side. But remember, this side has too many holes, right? So there are too many holes on this side, and there are too many electrons on this side, and the density is so high that the holes which move towards the right, which move towards the right, so you have negative ions here, right? Negative ions, and you have a positive ionic side on this side. This is what happens. I have deliberately drawn only one layer of mobile ions, because immobile ions, to save time, but you could have multiple layers. Now what happens is, since there are too many holes, the moment a negative ion is created, right, a hole comes in, let me enlarge this figure so that you get more clarity on the process of what happens in heavy doping. Okay, so in the case of heavy doping, when the hole approaches the depletion layer, okay, and the depletion layer, so because of the very heavy doping, you have too many of holes coming. As soon as a negative ion, which is immobile side of the thing, in the depletion layer, a hole comes in, and neutralizes this, right? The negative aspect of it. And similarly, you have electrons coming in from the left hand side. So you have too many electrons, right? So a very unlike a standardly doped p-n junction diode, you have too many electrons on the left hand side. Okay, so these are the electrons which want to move. They're coming from where? They're coming from the pentavalent impurity, the free electrons which are in the conduction band. They want to move. What they encounter is a positive layer of ions, right? So this electron generally would cross over, and reach the other side. Depletion layer starts happening, and there is a complete depletion here, and no electrons and holes are present here, right? So in the depletion layer, the number of electrons and holes is 0. Here, what is happening is, as soon as a positive ion gets created, since there are too many electrons, another electron comes in and neutralizes this. So this ion gets cancelled, okay? Because it has another electron available to it because of excess number of electrons. The consequence of excess holes and the consequence of excess electron is that these ions, right, get neutralized very fast, right? Finally, what will happen is the layer of ions, for example, if this was a two-layer situation. So you initially had, a normal diode, and you had two layers. Okay, so I'm talking about normal diode, which means it is not heavily doped. And now what you're doing is I'm just showing you the normal diode first, which has two layers of ions in it. Okay, so let's say there are two layers. On the left hand side, I did show you one, but now I'm showing you two layers. The overabundance of holes will cancel out one of the layers, hypothetically. So this whole layer will get crushed, and then maybe this whole layer also gets finished, because oversupply of electrons. So the holes are neutralizing the immobile ions, which are positive ions, and the electrons are neutralizing the negative ions which are there on the p side, right? So these are the ions being referred to in the depletion. So what happens finally? The width of the depletion zone reduces. Okay, now this is a situation of heavy doping, because the heavy doping neutralized this layer, okay, which I'm showing you. Okay, I did not show you two layer, the immobile layers, but now finally I had to, because I had to show you the cancellation. This also gets cancelled. So if you have a p-n junction diode being created with heavy doping, what you end up is getting a smaller depletion layer, which means heavier is the doping. The heavier is the doping, smaller, okay, smaller is the depletion layer. Just understand this. I mean, in our class 12, we don't have the formulas and all that, but if you go and study advanced level physics, you will find that there are formulas written where the width of the depletion layer is inversely proportional to square root of concentration of the doping you have done, right? So the doping, it does depend on doping. Okay, so if doping is very high in a p-n junction semi-diode on p side and n side, the width will become very small. This is the reason, because you're cancelling out the positive and negative, right? Now, how does it all link to breakdown? The first thing was to understand that heavy doping will result in a smaller in a smaller depletion zone. So if you go back and look into the question, you will see the words like doping and depletion written together, right? And if you read that carefully, gradually we're moving towards answers. Now let me go back, and I hope this is clear that why excessive number of holes and electrons result in a smaller depletion zone, because they neutralize the immobile ion layer and the depletion layer becomes very small. Now imagine a situation where you have a diode. Okay, you have a diode. So you have a diode, okay? And now this diode is heavily doped, which means compared to a normal diode, the depletion layer automatically is going to be a very narrow one. So let me just deliberately draw a very narrow one. And now, since this is P and this is N, let me reverse bias it. Okay, let me just reverse bias it. And when I reverse bias it, okay, when I reverse bias it, let me just show you the reverse bias part of it. When I reverse bias it, what happens? Okay, I'm just drawing the circuit. So you know how to do show the reverse bias. The negative terminal is connected to P and the positive terminal is connected to N. So this is your kind of the N. Okay. Now what happens? If you concentrate on this diagram, this already is very narrow. Okay. Very narrow one, right? Very narrow, right? So the width is very small. Width is very small, right? If you remember, E is electric field, right? Finally, definitely the voltage increased, because of the external voltage provided by the battery and the internal electric field which exists. There is a small depletion rate. Even this will have a junction potential and a small electric field. And it also depends on the width, dV by dx, right? If the width has become very narrow, right? If the width has become very narrow, electric field is high because the electric field is because of two reasons. The internal electric field, right, is because of the depletion layer. The electric field which is external, provided by whom? Provided by the battery, the external source of voltage. However, notice that the width is also very small, right? So the overall impact is that the whatever potential gradient that you create, which is delta V here, right, which is because of the impact of the reverse voltage. So this is your reverse voltage and the inherent voltage, right? Both of them, are now being felt across a very small region. And therefore, you also understand a smaller depletion region also means that the barrier is very small, right? The barrier size has gone down. So even the resistance is low. The barrier to overcome is very small now, right? So the barrier is also very small. The barrier is also very small, So if you do a reverse bias and you have, the high electric field because the width is very small, you can see electric field is inversely proportional to the width, right? Smaller is the width, of extremely high electric field gets generated. This extremely high electric field, whatever little immobile ions are left in a heavily doped situation. So let me just enlarge it and say, this is your situation, and you have in this depletion zone which you see, this is your depletion zone, right? So this is your depletion zone. In this depletion zone, you still have immobile ions, right? So the P side has some negative ions which are available here. So these are the negative ions which are existing here. And on the other side of the story, okay, so sorry, I should not have drawn it here. I will just rub this off. It cannot be outside the, so let me just rub these off. They are inside the potential, the depletion layer region. So you have a lot of negative ions here, right? So these, I have already explained you what is the impact of electric field. So this electric field will strip off the electrons from the immobile charges, right? We have already learned how the immobile charges, which are negative and positive, lose electron, and there is a sudden breakdown or a extra current that flows. You can watch the previous lesson. We talked about this, that the high, but remember, this is happening because of high electric field, and high electric field is happening because of a very narrow depletion region. That the narrow depletion region is because of high doping, right? So if you look and go back to the question and read the question, you will find words like doping, depletion layer, and all of that. We will go and attack that choice also. But remember, you must understand that electric field is very high now because of the lower depletion region. The depletion region is very small because of very high doping. Very high doping results in a lowered depletion zone width because of overabundance. I hope this is making sense. And now you can see the diagram, right? The first diagram is light doping. The junction width, which is the depletion width actually, around the junction is wider. And you can see the second diagram where the PN diode is heavily doped. And we have just discussed why heavy doping results in a smaller width of the depletion zone. So this is the crux of what we have learned so far again. So doping has also been included as one of the things that impacts breakdown. How and why, we will learn it very soon. Now, if you look into this diagram, the light doping and heavy doping, the question arises, does the breakdown happen in the case of light doping, or does the breakdown only happen in heavy doping? See, the answer to this question is that the breakdown happens for both the situations. You can have both these types of diodes with low doping and high doping reverse biased. You will still get a breakdown here, and you will also get a breakdown in the case of heavy doping. So breakdown is going to happen in both the situations. This is confirmed. Don't worry about it, right? But the type of breakdown which happens in light doping, the way it happens, and the way it happens in heavy doping scenarios, these two are different types of PN junction diode breakdowns. And we will study now how the breakdown which happens in a light doping compares with the breakdown of the PN junction diode that happens in the heavy doping. So let's start the next lesson where we compare the details of breakdown in light doping scenario and the details of the breakdown in the heavy doping scenario. Thanks. Making sense. And now you can see the diagram, right? The first diagram is light doping. The junction width, which is the depletion width actually, around the junction is wider. And you can see the second diagram where the PN diode is heavily doped. And we have just discussed why heavy doping results in a smaller width of the depletion zone. So this is the crux of what we have learned so far again. So doping has also been included as one of the things that impacts breakdown. How and why, we will learn it very soon. Now, if you look into this diagram, the light doping and heavy doping, the question arises, does the breakdown happen in the case of light doping, or does the breakdown only happen in heavy doping? See, the answer to this question is that the breakdown happens for both the situations. You can have both these types of diodes with low doping and high doping reverse biased. You will still get a breakdown here, and you will also get a breakdown in the case of heavy doping. So breakdown is going to happen in both the situations. This is confirmed. Don't worry about it, right? But the type of breakdown which happens in light doping, the way it happens, and the way it happens in heavy doping scenarios, these two are different types of PN junction diode breakdowns. And we will study now how the breakdown which happens in a light doping compares with the breakdown of the PN junction diode that happens in the heavy doping. So let's start the next lesson where we compare the details of breakdown in light doping scenario and the details of the breakdown in the heavy doping scenario. Thanks. Just a quick reminder. So when you do the reverse biasing of a light doped PN junction, so I'll just show you how I do this. I anyway connect a battery always, right? So I will just connect a battery to the light doped PN junction diode, and you know how do I connect this? So I will just quickly do this so that we save on time. So this is the reverse biasing of the lightly doped PN junction diode, and let me reverse bias the heavily doped reverse bias to the heavily doped PN junction diode, right? So let me just connect this, and this is the doping we are doing, okay? And all right, so this is also reverse bias, right? So this is now the point I'm trying to tell you here is, see, finally, what you need is the sudden current. That's your goal, right? You need sudden current due to what? Due to minority carriers. Major carriers which are in the forward bias will not exist here because it is not forward bias, right? Forward bias was, we discussed the forward bias initially. The carriers in the case of forward bias are the majority carriers. But in the case of the reverse biasing, what we want is some addition to the drift current. So sudden current which we want should be an additive to the drift current. And therefore, the sudden current should also be made up of minority carriers. And you remember, the drift current is also made up of minority carriers, which are very limited, and saturation is attained. So that is why the current is called as saturation current or the reverse saturation current. Why I told you this? Because finally, even though you are light or heavy, whatever type of doping you have, your final goal is to have the sudden rush of current in the diode. And we are going to study now how the sudden rush of current is attained in the case of light doping versus how it is attained in the case of heavy doping. So let's start the lesson. I just wanted to fill in this blank so that you have in your mind a picture and a story getting prepared and you're ready for the final lesson. Right, so let's start the discussion with the first type of scenario, which is that of a light doping. So what we are studying is a lightly doped semiconductor. And all right, so let's start the concept with the heavy doping. Okay, so we are starting this with heavy doping. Let me just do a reverse bias of this quickly. So this side is P and this side is N. And let me just do a quick circuit completion. This is my negative, this is my positive, and this is the scenario of heavy doping. Okay, so I think just assume the wire is here, okay, and ignore the upper part of the wire. All right, so ignore this part. Okay, now we are discussing heavy doping. Okay, so the concept of breakdown in heavy doping. See, remember, in a heavy doping, what you have is a thin depletion zone, right? So I will just draw a line, and around this, what you have is the immobile ions, right? So you have negative ions here, okay, and what you have on the other side is the positive ions, okay. You have a positive ion. What you do is you apply the V reverse bias, right? V reverse bias. Okay, when you do V reverse bias, the electric field which is generated, as we know, is very high because the depletion layer is very, very small, right? The electric field strips off the electrons from the ions themselves. So if you see this is your negative ion, right? So if you remember, this was negative. So this side was negative and this side had positive ions. So these ions are stripped of electrons due to the presence of the V reverse. Okay, so this is a normal reverse bias voltage which you have applied it strips off. And if you remember, if you go back to my lecture, you would have listened to me talking about this stripping off of the electron. So the strip off of electron happens in the depletion layer. So whatever stripping is happening, so ions the immobile ions lose electrons, okay, in the depletion zone. In the depletion zone. And I had talked about it, okay. I did not tell you what's happening at that point of time. It was a general discussion. So I just discussed one of the ways the PN junction breakdown happens, okay. Now, the at this point of time, the voltage you've applied is normal, okay. And I will tell you why I'm using the word normal. So a normal voltage is applied. A normal voltage results in a very high electric field. The electric field is very high because of the small depletion width. So the width of depletion is very small. The width of small depletion is because of the heavy doping, right? We've already studied this. Heavy doping results in very small width. Very small width results in very high electric field. Even though the voltage you've applied is a normal voltage, this is reverse bias voltage. So don't forget, this is the reverse, and therefore the electrons get stripped from the depletion layer, and these electrons then start flowing with the drift carriers, minority carriers. Remember that we have minority carriers always constituting. So the electrons which were in minority here, so there were electrons which are in minority here and holes which were in minority here. These constituted the drift current, and they're independent of the voltage, right? So the drift current is a saturation current, and because of the limitation imposed by the quantity of minority carriers in P and N respectively, there's a limitation. And now what you have is a sudden increase in number of electrons coming from the ions, okay, the immobile ions located in the depletion zone. This is a zone where immobile ions are located, negative and positive. They provide electrons. Now, the moment they provide electrons, what happens is the electrons start moving in towards the positive terminal of the battery, which means the current is in this direction. And therefore, the earlier the current was also in this direction, because the drift current on account of the minority carriers happens in this direction. So now you have a drift current which was because of the minority carriers, which is ID, and now you have a current here which is due to the rush. Okay, so due to the rush, tremendous rush is going to happen because you're stripping the ions of their electrons, right? And now you have the breakdown happening at a certain voltage. When you start increasing the reverse voltage, a particular point comes in, and if you look into the graph, this is what happens. Okay, this is what happens. We have already studied this. You have some initial current which stays constant for a while, and is called is a saturation current. And then of course, this current starts falling very rapidly. Okay, and this is what is called as the breakdown. So we talked about knee at that point of time. At that point of time, when we studied this earlier in the lesson, the previous lessons, we did not say anything about doping, but now we got into the reasoning, and now we are dividing the types of breakdown. So this breakdown is the breakdown which is happening for a heavily doped PN junction. P and N both are heavily doped, and there is a very thin layer of depletion layer. So I hope this heavily doped, how it happens is with the help of a small depletion layer and a normal voltage, but the final outcome is a very high electric field. High electric field is required to strip off the electrons from the depletion layer. So I hope this is clear to you, and I will just label it. This is the case of PN junction diode. This is a case of PN junction diode breakdown. So a breakdown happens. Breakdown when the doping is very high. So doping is high. Doping is high. Additionally, what are the important points? The voltage is normal. Okay, the voltage is normal. So the voltage you're applying here, obviously it reaches a certain place, which is at this knee, where the sudden rush of current happens. But this voltage, whatever you apply, is a normal voltage. So voltage is normal. Voltage is not very high, it is normal. Electric field is definitely quite high. Okay, and the depletion layer is very small. All the points are connected. Low depletion layer, as I explained you here, right? High doping, low depletion layer, high electric field, although the V is very small, but because of the small width, the the you know the electric field is very high, and this electric field finally results in stripping off of the electrons from the ions, that results in a sudden rush, and this is called as a breakdown. If you increase the voltage further, nothing happens. The the current just keeps on increasing without increasing further voltage. Just a small summary of whatever we discussed for the high doping scenario. Let's move on to the next one, which is the low doping scenario. In the low doping scenario, we discussed what will happen. You again will have an opportunity for the breakdown. But let me explain you how, in the case of low doping, the breakdown happens, right? Not that you can't have breakdown in low doping. You can still have breakdown in the case of low doping. Let me just draw a simple diagram. This time what I will do, I will draw a relatively wider depletion zone because my doping is normal, right? It is not very high. This is a case of normal doping. Okay, so normal doping. So when you have normal doping, what happens in the case of normal doping? Let's talk about it. Okay. So let me just explain you what happens in the case of normal doping. Now, when you have normal doping, okay, so let me draw the junction. Normal doping will not give you a breakdown just like that. I have a normal doping, breakdown should happen. No, it will not. Let me first reverse bias this, and I will tell you what is a special condition you need for the breakdown of a normally doped semiconductor. Let me just, so this is my P side, so I will connect a negative, positive to the N side, and now this is reverse biased. Okay. Yeah, it is time consuming to draw the circuit again and again, but just bear with me. All right, so this is your P side and N side. Now, when you have normal doping, I said breakdown will not happen with normal doping. Why? I will tell you the reason. When you do normal doping, you will have to increase the voltage. Okay. So if somebody gives you a PN junction diode with normal doping and he says, do an experiment where you are able to show the breakdown, you have to tell him, I will increase the voltage. So the reverse bias voltage, which is applied in the case of normal doping, is very high. Okay, you need a very high voltage, reverse bias voltage, in the case of the normal doping scenarios. And what happens because of this very high voltage is that the kinetic energy, okay, the kinetic energy which the electrons gain, okay, the kinetic energy which the electrons gain becomes very high. So what happens when the kinetic energy of the free electron, supposingly there is an electron which is freely available, on the side of the P. So there is an electron which is available as a free electron, and this gains kinetic energy. It goes and strikes a boron atom. Okay, so the boron atom gets struck with an electron like this. Now, this particular collision between the electron and the boron atom, right? It strikes like this. This is what happens. So the boron is now going to lose an electron. So boron loses an electron because of this collision. So you have a generation of an electron from the boron atom, right? So an electron gets created and a hole also gets created in the boron. So boron gets a hole. So what is happening in this part of the world is the free electrons gain a lot of energy. They strike the atoms on either side. So here also, if you have a phosphorus, the free electron comes and strikes, and the phosphorus in turn loses an electron, and a hole is left behind. So in this whole process, the electron and hole pair is getting generated, okay? And these electron hole pair, so electron hole pair is getting added. Lots of them get added, and because of the reverse bias, they travel in a particular manner, which is what the electrons are definitely going to move towards this direction. But now remember, the most of the action is happening on the p side and n side, and the electrons are very high energy electrons, which are being used to knock off electrons. In the previous case, when the doping was very low, sorry, the doping was very high, in high doping, all the action was happening in the depletion layer. Here the action is not happening in depletion layer. The stripping of electrons is happening on either side, both the sides it is happening, and therefore what happens is the holes are going to travel in this direction. So you will find that the overall direction of the current, if the electron is moving in this direction, the overall direction of the current is this. Again, what is happening is you have a sudden rush of current which is in this direction, which adds to the drift current. So this is your sudden current which is coming into picture, right? So I hope you have understood that in the case of normal doping, what you have to do, you have to start with a very high voltage. Start with very high voltage, okay? When you have very high voltage, the carriers which are there, the electrons, the free electrons, they go and strike the atoms and strip them off the electrons, and hole is left. And remember, when you apply very high voltage, the depletion layer is pretty wide because it's a normal doping, right? Only in the case of heavy doping, you can get a small depletion. So depletion layer is very small, right? And depletion layer is small in the case of heavy doping. In the case of normal doping, depletion layer is the usual depletion layer, and the depletion layer, and the high voltage results in a high electric field, okay? And but that electric field is not stripping off the electrons from the ions at that point of time. It is not that high as compared to what it was in the heavily doped situation. In the normal doping, the action is happening on the left and right hand side because of so a very high voltage actually coupled with a depletion layer which is wide results in what? It results in finally stripping off of the electrons and creation of carriers with a lot of kinetic energy, which then collide with the atoms, and more electron holes pairs get created, and they constitute towards the sudden rush of the current. So I rush, I would call it I sudden break. So this is the breakdown being referred to, and here also similar diagram is going to happen. The only difference is that the diagram is going to get bit different as compared to the previous diagram of high doping, and I will show you how the diagram is different. So if you were to do the experiment with high doping and low doping, this is the way the experiment needs to be done, okay? Or theoretically, I'm saying if you do this in laboratory, okay? So you can get a sudden rush, V reverse. If you have heavy doping, you will get the breakdown very fast. If you have light doping, I told you the voltage has to be slightly higher, and the breakdown will happen late, okay? So this is your breakdown which happens at this point where, and this is for, so this breakdown is for your heavy doping, and this breakdown is for normal doping. The doping is normal, but the voltage has become very high, and you can see the voltage in the first case is only this much with heavy doping, and the voltage in this case is this big, okay? So the voltage of heavy doping voltage is less than the voltage of normal doping. When I say this, I mean the knee part of it, right? Where actually the rush of current starts. Both are breakdowns, but both the breakdowns are happening at different places. All right, now we have clarity on all the topics we started with, right? We studied the breakdown. We studied two types of breakdowns. We understood how does doping help. If doping is not available, how does the high voltage help? And what is the role of depletion layer size and how it impacts the electric field creation, so on and so forth, right? But broadly, there are two types of dopings which are there. That is the starting point of the reverse biased PN junction. So let's study each one of them. Okay, choices. Choice number A, large velocity of the minority charge carriers if the doping concentration is small, which means the normal, right? The normal one. In the normal doping scenario, which we just studied, in the case of normal doping, what was so special, right? The high voltage was used. High voltage resulted in what? High voltage resulted in kinetic energy, which means high velocity of the electrons. And the high velocity of electrons resulted in collision with the atom, which resulted in generation of another electron out of it, leaving behind an ion, right? So a lot of extra electrons, free electrons start getting generated because of multiple collisions happening inside the lattice. So this is right? That large velocity is the likelihood increases if you have, the velocity of the minority charge carriers is very high. When this large velocity, automatically, generally the reference is to the electrons, because electrons constitute the current. Holes also get created and they take part in this. So we can say yes, both. So the rate at which the electron moves is generally considered to be the thumb rule. So answer number A is correct. If the doping concentration is large, you don't need large velocity, right? If the doping concentration is large, what you need is essentially a very high electric field because when the doping is very high, right? So let's say we are now choosing between these two, right? If the doping concentration is very large, right? So this is the scenario number one, which I discussed. The doping is very large. Large doping resulted in what? It resulted in thin depletion layer. And what did thin depletion layer do? Thin depletion layer resulted in the high electric field. The high electric field resulted in stripping of electrons available in the ions, and those electrons then constituted the sudden rush of current, right? So choice number D is also right. So A is a different type of breakdown and D is a different type of breakdown based on the doping, and then one is based on large velocity, the other is based on strong electric field. We have studied both of them. I hope it is clear to you why choice and A and D are the correct choices. The video does not end here. I am going to now summarize the learning. My idea was not to tell you the solution, which you can see anywhere, but this level of detail and explanation is not available in the whole of internet. So watch my videos very carefully. They're long, short, medium type. Don't worry about them. Take a 10-minute break every time you see my long video so that you can absorb the points. Maybe you can see it by lesson. Take a break and again go back and see the concept. I'm going to summarize this whole discussion very shortly. So hold on. I hope the answer is clear to you. And the reasoning has been given to you all this while I've taken, I think, around 70 minutes to give you explanation and 2 minutes to give you the answer. Most of the places you will find a 2-minute answer and that's it. Because there is no aim to teach you so that you become good learners and you're able to solve the problems without any help. Let me go to the next part of it, which is the last part. I'm going to summarize whatever you have learned and I'm going to give it some names so that it helps you memorize all of this easily. Let's move into the next part of the video. So as promised, this is the summary of whatever we have learned. So the two types of breakdowns we studied were actually the avalanche diode breakdown, which is more popular and most common type of breakdown of a diode. But Zener diode is also popular. It depends on the application. Okay, depends on the usage. See the difference. Avalanche diode breakdown is based on high velocity of charge carriers. The Zener diode is based on high doping levels. You get the same result using the high doping levels. Second point I think is very clear in your mind, that in the case of avalanche, because the doping is poor, you increase the reverse voltage and you get high velocity. So second is actually the reason why you have high velocity of charge carriers, high voltage. And in the case of Zener diode, the doping is very high, but the reverse voltage is low. Third is bit difficult for you, the tunneling of electrons from p side valence band to n type conduction band. This means that the electrons which are on the p side, where the collisions happen, in the case of avalanche, the electrons that come out have to reach the conduction band level finally, right? If the electron is stripped off from valence band, for it to participate in electricity, it should reach the conduction band. So tunneling is not in our course, so don't worry about it. Just you can have a sense that electrons from the p side, which are there in, have to move to the n type conduction band, okay, from the valence band in the p side. And in the case of Zener diode breakdown, the strong electric field, right, it pulls the electrons from the ion. You can see the last point of the Zener diode, one and the same thing. And then of course the avalanche diode breakdown, the depletion layer is wide because the doping is poor. The Zener diode doping is very high on both the sides. We will not get into a lot of detail about doping for your class. Both the sides are equally doped, heavily doped. The depletion layer is very small therefore. Last is collisions, which is high velocity, is responsible to get you free electron or charge carriers for the sudden rush. But in the case of Zener diode, the high electric field in the depletion region results in stripping of electrons from the ions. So now you know the names also. Whatever we discussed, that type of breakdown had a name. The first thing we discussed was Zener diode breakdown. The second thing which I discussed as a normal doping was a avalanche diode breakdown. Thank you very much for your patience. But I can assure you, you listen to these videos, you don't have to go anywhere. Anywhere means you don't have to go to a classroom. You don't have to join any application, pay anywhere. You can get the answers of so many questions on my YouTube channel. I have close to now 2000 videos already running. Watch them. And I'm also improving because I'm not a professional YouTuber. I only know physics, but I'm learning the skills of a YouTuber, how to become popular and etc. etc. A lot of people have given me feedback on working on thumbnails and all of that. So I'm learning that. Thank you all of you for the excellent WhatsApp messages you have given to me on the quality of work I'm doing. And thank you very much for subscribing to my videos. I'm very grateful to all of you. Thank you very much. Don't forget to subscribe to this channel because you're going to see some explosively beautiful videos coming out of this. Thank you and have a very good day.